Now let's move to array detectors. So one type of array detector is what's known as a photodiode array. And this is basically just the same idea as the infrared detectors we were just looking at, where we have a semiconductor material with a band gap. The band gap here is usually silicon, which is sort of visible range detection. And instead of just having one of them, we have a whole array of them. So something like 50 or 128, or usually pretty large numbers of what are known as pixels, individual pixels that we can measure light with. And so the idea is that we have silicon, we have this PN junction, and this is sensitive to light. That's, again, the specific details of the semiconductor materials are, they are important, but not for our class here. If you are interested, there's a lot of really fascinating material about learning how semiconductors work and P and N type semiconductors and things like that. Some of you may have learned about some of this already. But each of these can detect light separately, and as electrons are generated, the electrons can be measured individually for each pixel. And so this is basically like you have 128 or whatever individual detectors, but they're all right next to each other and they can all measure simultaneously. And so the advantage of using array detectors is, for example, instead of needing a monochromator, you use a diffraction grating and you split up all your light into all the different angles, and you just measure all of the wavelengths simultaneously. And that's probably the most common use for an array detector in a spectrophotometer, is that we no longer need a monochromator. We have what's called a polychromator instead. We split up the light and measure everything all at once. And so that leads to big advantages in terms of acquisition time. You don't have to scan a diffraction grating. You don't have to actually turn it to get the different wavelengths of light. You can instead acquire the entire spectrum simultaneously. So much faster acquisition times, no moving parts. Some possible disadvantages is these are not as sensitive as the PMT because you lack the multiplication steps that you get with the PMT. And the other thing is the resolution may suffer depending on your details. So it depends on your grading as well as your spacing between your different pixels on your photodiode array, how good of your resolution can be with a polychromator, set up with an array detector. One final type of array detector we'll talk about here, very briefly and not get into a lot of the details, is what's known as a charge coupled device, or CCD. Now, instead of this being a line of pixels, this is now a rectangle of pixels, or a square. Often it's a rectangle, though. And each of these pixels is similar to what we just showed on the previous slide, where we have some PN junction, and we have light that generates electrons, and we kind of store those electrons in each of these, what's known as a pixel, again. And so each of these pixels can detect light, and the way, after a certain amount of time, we read out how many electrons were generated at that specific pixel. And so CCDs were very commonly used in cameras, digital cameras, when they first came about, and they can be used, and they are still often used for scientific purposes where we need to measure an image of something. Instead of just measuring, say, a spectrum, we're measuring how do photons, are generated in sort of a two-dimensional pattern. Whether that's taking a picture of something or measure, if we can disperse wavelengths in two directions, we can get things spread out in a rectangle or a square instead of along a line. And so we can use the CCD to measure all of those simultaneously. Similar technology is used in your cameras, in your smartphones, or if nobody has them anymore, but like standalone digital cameras. It's a similar idea, except for slightly different in terms of the technical details. It's known as CMOS, complementary metal oxide sensor. And in a CCD, like is shown here, we kind of read off each pixel individually. And so once we have acquired our image for as long as we want to, say half a second or something, or less than that, we read off all of the numbers of electrons for each pixel in this multiplication stage and output amplifier. So the image has to be slowly transferred off of your CCD, kind of row by row, pixel by pixel. The CMOS, I don't have a picture of it here, but each pixel can be read off simultaneously. And so they each have their own amplification built in. And so you can get the image off much quicker. They use less energy than a CCD. And so that's why they become much more common in smartphones, because they use much less power. And so when you want your battery life to be as long as possible, you don't want people complaining when they take a bunch of pictures and their batteries suddenly dying. And so CMOS has kind of become the industry standard for the similar idea of being able to measure an image instead of just measuring light at one particular pixel. And so this is another type of detector that's very common in spectrophotometers where you need to be able to see a whole image.